In the second part of this course, we're going to start taking a look at the idea of being able to work with functions of more than one variable. In Calc 1 and Calc 2, we took a look at functions of single variables, and we were able to find derivatives and integrals of those. In pre-calculus, we found domains, ranges, different types of things that we could do with functions in one variable. In Calc 3, we're going to start taking a look at everything that we've done in Calc 1, 2, and pre-calculus, and now we're going to apply it to functions of more than one variable. A function of two variables essentially has an input of an xy and an output of z. So whenever we have the notation fx comma y is equal to z, that's sort of like f of x equals y in two dimensions. The domain is going to be all the ordered pairs, not single variables, but now paired variables, that generate a real number for z. The range is all the possible outputs that z might assume. X and y are independent, and z is dependent. Now, a lot of times these are difficult to be able to plot. So what we like to do is we like to use an online resource. And I found a pretty good one that's free here at this Geogebra website. So it's a little bit different than Desmos, but it does the same thing. So what we're going to do is we're just going to take a look at some basic pre-calculus type of stuff initially to be able to see what each of these functions might look like and to describe some of the characteristics. So for each of the following functions, we want to do four things. We want to find f at 1, 1. We want to find the domain of f. We want to find the range of f, and then we want to graph f. So f at 1, 1. As easy as this might be, but just to make sure we understand it, I'm going to substitute 1 for x, I'm going to substitute 1 for y, and then I'm going to evaluate. So f at 1, 1 is 10, and remember this is the z value. So essentially what this means is that we have the point 1, 1, 10 that falls somewhere on the graph of f. The domain, okay, so this is part II. This is part I. The domain is all the numbers that we can put in for x and y. And notice that it's a polynomial. So, since we have a polynomial, what we're going to say is that x and y, such that x and y are elements of the real numbers. All right, so that's how we're going to define the domain D. Right. Now, the range is a little bit different. Notice that no matter what numbers we plug in for x and y, the lowest possible number for this would be 0. Right? Anything else, like if we plugged in a -1 and a +1, or a -2 and a -2, we'd start getting a bigger value that's positive. All right? So for the range for this, R, we're going to say that z is going to be an element of 0, which is the smallest possible number inside of our function, to infinity. Right? And then the last thing we're going to do is we're just going to plot the graph of this. All right? Now what I'm going to do is I'm going to plot it on a separate screen, and then I'm going to try to import it for you so that way you can see what the graph looks like for each of these. So if you'll just bear with me for a moment as I do this. We have z equals x squared plus y squared. We're going to plot that. And it looks like it's going to end up being a paraboloid. I'm going to take a screenshot of this. And I'm going to paste it into the graph. So just again, give me a moment so that way I can plot this onto what you'll need to see. It's not going to be too difficult. All right. And this is what the Geogebra Graphics should look like. All right. And you could probably go here and do it yourself just to verify. In fact, I would encourage you to do that. All right. And here's what the graph looks like. I'm going to shrink it a little bit just so we can have it in the same context. All right, and so what we have is we just have an elliptic paraboloid, concave up, as we would expect. And remember, this is going to have the equation z equals x squared plus y squared. And if you go back to that quadratic surfaces sheet that we looked at earlier in the course, then you could probably see that this is going to be exactly that, an elliptic paraboloid concave up. All right, so that's one example. All right. Again, make sure you use this website, this Geogebra, to help you to be able to graph these fairly easily. Let's do this again for a couple more problems. So a second example, this time we have a natural log in 2 dimensions. So we have, or 3 dimensions, excuse me. So we have ln of x plus y minus 1. So we're going to substitute 1, 1. So we're going to have f at 1, 1. That's going to be ln of 1 plus 1 minus 1. And we know that's ln of 1, which is 0. So that means the point 1, 1, 0 is somewhere on this curve. Second thing we need is we need the domain for this function. Now we remember that for the natural logarithmic function, that whatever's inside the parentheses has to be bigger than 0. Right? So let's just go way back to pre-calculus. And the interior composition of a natural log cannot be 0, cannot be less than 0. So there's a couple ways to describe this. So for the domain, what we're going to say is that the domain is all ordered pairs x, y, such that x plus y is greater than 1. And that's not the only way to express this, but that might be the easiest way to express it. A third part of this problem is being able to find the range. Think back to pre-calculus. What is the range for natural log? Well, a natural log function looks like this, essentially. All right, it's probably not as, it's probably a little bit more slope than that as we get a little bit closer towards infinity, but regardless, that's the basic characteristic. And we remember that the range for natural log goes from negative infinity to positive infinity, and that's the same thing in 3 dimensions. In 3 dimensions, we're just going to extend this, and we're probably going to have something that looks like this. Okay, we'll see in a moment when we graph it. All right, but notice that the z value in 3 dimensions just keeps getting bigger and bigger. So in this case, z is going to be an element of real numbers, or if you wanted to write it as an interval, negative to positive infinity. All right. Just like I did before, I'm going to plot this using Geogebra, and I'm going to cut out a picture of it. So just give me a moment, so that way I can go ahead and plot this for you all. And I'm angling this so that way you can get a good look as to what it looks like, or at least a good image as to what this thing looks like. All right, so and then I have to cut and paste it, and I have to cut it again. So it's a little bit of a roundabout way of doing it, but it works. All right, almost there. Alright, finally I'm going to paste this. And this is what our natural log function looks like. Alright, not surprising. And if you'll notice that there's a bunch of values that don't exist, and essentially what we're saying is, like right along here, anything in back of that, that's when x plus y is less than or equal to 1. Everything else, it's going to exist. And I want you to notice that the z value is just going to continue to get bigger infinitesimally. All right, so that substantiates our guess that it is going to be negative to positive infinity for the range of this. Okay, one final example. This time we have root x plus root y. All right, so maybe pause the video here. All right, give it an opportunity to see if you can figure that out for yourself, and then come back to see if you are correct with this. And in the meantime, I'm going to go ahead and work this through. So f at 1, 1, that's really easy. That's root 1 plus root 1, which is 2. And again, that means that the point 1, 1, 2 is a point somewhere on this function. The domain for this. We know that for square root functions, x in this case has to be greater than or equal to 0. Y has to be greater than or equal to 0. So we're saying all ordered pairs x, y, such that x greater than or equal to 0, y greater than or equal to 0. For the range, this is very similar to the problem that we saw earlier, all right, with the elliptic paraboloid. Notice that we can never have any negative numbers as an output for this function. We could certainly have 0, because if we substitute 0 back in for x and y, that would be an output of 0. Every other number that we substitute in, any other ordered pair, is going to give us a value bigger than 0. So the range for this is going to be that z is an element of 0 to infinity. All right, and that should be a hard bracket. Sorry, marker slipped. And then, just like the previous two, I'm going to go ahead, graph this. All right, so just give me one moment while I graph this. And maybe think about what it might look like beforehand. And I'm going to print the screen, and I'm going to cut and paste it. Almost there. And then finally, we can paste it into the Word doc. And this is the graph that we get out of it. All right, so notice that what happens is it starts at the origin 0, 0, 0. Right? And it just keeps getting bigger from there. Notice that all the values are in the first octant. Okay, meaning that z is not negative, x is non-negative, y is non-negative. All right, so it just makes sense that our domain and range must be correct for this problem. All right, so hopefully this gives you a good overview as to functions in two variables and our 3D graphs, how to plot them. In the next section, what we're going to do is we're going to start taking a look at some of the principles of these types of functions in two variables.